In this video, we're going to talk about linear functions. We're going to talk about linear functions. And to start off, we're going to look at these two tables here. And we want to notice the difference in the patterns in the inputs and outputs of the tables given below. Now, if you look at these patterns, notice that the x values are the same in both tables, right? And notice that we also have functions in both tables because each input corresponds to exactly one output. The difference is in how the y values or the output values change, right? In that first table, I have 1, 3, 9, 27, and 81. And in that second table, I have 1, 3, 5, 7, 9, which you know are your first few odd numbers. And so the main difference that I can see, and it's probably easier to see the differences in the second table, right? Because what we're doing here is to go from one y value to the next, there's an addition of 2 units. From 3 to 5 is 2 units. From 5 to 7, I add 2 units to 5, I get 7. Add 2 units to 7, I get 9, right? So there's an addition of 2 units. In the table above, there's actually a product or a multiplication times 3. 1 times 3 is 3. 3 times 3 is 9. 9 times 3 is 27. 27 times 3 is 81. And so here our y values are an additional multiplication by 3, but in our table below, our y values from one successive to the next is an addition by 2. Now, if I think about what these graphs are going to look like, notice how these y values are changing. Oh, I go up by 3, then I go up by 6, then I'm jumping up by like 18, then I'm jumping up to 81. That's a lot. That's a huge number. This graph is going to look something like this. And what we're going to say about this graph below is that, oh, I'm going up to each amount, the same amount each time, a constant value each time. I'm adding the same number. And so with a 1 unit change in x, my y value is always changing by y, by 2, right? And in our xy plane, our x values changing is a horizontal change, right? So if I start at one x value and I change 1 unit, and then I change y values by 2 units or add 2 to the previous y value, I get here. I go 1 unit by x, I go the same number of y value units there, I get there, so on and so forth. And what we're going to see is that our actual graph is going to create a geometric figure that we're very used to seeing, which is a line. And so a graph or a chart or a table that looks like this, where our y values are increasing by a same number, by an addition or subtraction, we create a linear function. And when there's a multiplication by a constant, like we do in this chart above, it's a nonlinear function. And we'll talk later about the exact type of function that is, all right? And so we have a linear function in chart 2. And so what we're going to do is we want to actually graph the actual points in this graph. And notice I have an x coordinate of 0, y coordinate of 1. So I get the ordered pair 0, 1, have the ordered pair 1, 3, 2, 5, 3, 7, and 4, 9. And so I'm going to plot all of those points on this graph here, 0, 1. And as you can see, when I graph them, especially here, I do see that I have a linear function. It's going to make a straight line if I could draw an actual straight line. All right, and so we have a linear function. That's the geometrical representation of that data. And so if you want a definition of a linear function, it's a function whose graph is a straight line. One of the properties of linear functions that make it linear is that it has a constant slope, right? The slope of a linear function is always constant, all right? And to define the slope, we use the variable m, but a lot of people remember that it is rise over run. And by rise, I mean it's your change in your y coordinates, your vertical change, over your change in your x coordinate, or your input, horizontal, right? Some people write that as change in y over change in x. You can also write it as change in your output over your change in your input if you don't want to attach a variable to it. There's a formula for slope that we want to talk about here. I'm going to go back to this graph and I'm going to pick 2 random points, right? I'm going to pick this point right here and this point right here. I'm going to call this point x1, y sub 1. So that's x and y with a subscript of 1. And I'm going to call this one x sub 2 and y sub 2. I don't really care about their values, right? But if I want to talk about the change in y over the change in x, since we're in our x and y plane, then what I'm going to do is I'm going to draw and I'm going to figure out what the horizontal distance is between these 2 points, which is given here. And I'm going to think about the vertical distance between these 2 points here. This vertical distance is this y value here, which is larger, minus that y value there. All right, that's the vertical distance. And the horizontal distance is the difference between these x values. All right, and this point right here has the x value of x1. So it's going to be, sorry, x2. So it's going to be x2 minus an x1, and that'll give us that distance there. And this y2 minus y1 will give us that. And so if we want a formula for the slope of our line, we have a y2 minus y1 over x2 minus x1, all right? And that will give us the slope of any linear function. If I know 2 points that the linear function passes through, then I can put the x and y coordinates in this formula, and it'll be a calculation of our slope. There are ways that we can see or describe slopes of linear functions. I have 2 graphs here. In each of these cases, our linear function is behaving in a certain manner, right? So if I look at this function here, our linear function rises from left to right. Ooh. Another word for that is that it increases. All right, any line that has this feature has a positive slope. That means that m, which is the formula of the variable that we use for our slope, is greater than 0. All right. In this case, our graph of our line is falling from left to right. All right. And we always read things from left to right. And when something falls from left to right, we say that it decreases. And when things decrease, right, our slope is negative. In notation, that means m is less than 0. Our slope is less than 0 in this case. And in here, we have a graph where we're neither rising nor falling from left to right. And so we can say that we're constant from left to right. Well, when we're constant from left to right, that means we neither rise nor fall, so we have a constant. Neither increases nor decreases. We have a 0 slope. That means our slope equals 0. There's no rise. The rise over run is 0. And so we have a slope that's equal to 0. And so when we're talking about linear functions, these are the only 3 cases that we'll ever have. And so we don't have a vertical line because a vertical line is not representative of a function, because for each input, there's not exactly one output. All right, the interpretation of slope, right? The slope gives us a change in y over a change in x, right? And we'll simplify it with a simple number, right? When we start to think of slope in interpretations to real life problems, this is how I like to think about it, right? Your slope is a rate of change, right? It's a rate. It's a division of 2 quantities, a change in y over a change in x. Usually when we divide 2 quantities, we call it a rate. And since it's the change, the division of 2 changes, we call it a rate of change, right? It specifically tells us how much the output, or your y, increases or decreases for a 1 unit increase in your input. So let me go to this picture here, or this table here, right? Notice our x values are increasing by 1 unit, right? The slope is always kind of given with that understood, that there's a 1 unit increase in your input when we look at the number of the slope. And it tells you how much your output increases or decreases, all right? Another way that we can say this is that every time x increases by 1 unit, y increases by the slope, okay? And so in that graph where we have here, let's undo that. Let's redo that. and put it here. So every time we give a slope, we're the number of the slope. Now the rise over the run may come from using different numbers, like 2/3, right? We rise up 2 and we go to the right 3 if we're using 2/3, right? But the slope is basically telling me for a 1 unit increase in my x, the y value is increasing by that slope amount of units, all right? Some additional information about your linear functions is that we have a couple of equations of lines that we want to review. One of the equation of lines is the slope-intercept form of the equation of a line, which is given by y equals mx plus b. Here, our m equals the slope, and the b equals your vertical intercept. All right? And so if you know the y-coordinate of your vertical intercept, right, it's the y-coordinate of the output value of your vertical intercept, then you have your values that will give you the full equation of your line. Here, I have the point slope form of the equation of the line. It involves a point that this line passes through and the slope, right? So m, again, is your slope. And that y1, x1, y1, that is, I'm going to type this in here. That's equal to a point the line passes through. So if there's a point you know that your linear function contains or passes through, then you can plug in the x-coordinate here for x1, you can plug in the y-coordinate here for y1, and you can plug in the value of your slope, and you will have a formula for the equation of your line. Okay? And so what we're going to do here is we're going to find the equation of this line here, and then we're going to get to an application problem where we start to do some interpretations. So find the equation of the line that passes through the point 4, 5, and 2, 1. Now, I have two equations of a line here, and in both of those equations, I need to find the slope because that's m in the formula. This formula here has an m right here. This one has an m right here, right? So the first thing I'm going to do is I'm going to find my slope. And I remember that formula y2 minus y1 over x2 minus x1, right? I'm going to label this point x1, y1, and this one x sub 2, y sub 2, right? And so I'll replace these values in this function. I have a -1 minus 5 over a 2 minus 4. That'll give me a -6 divided by a -2, which equals 3. And so I know my slope is 3. And so what I'm going to do is I'm going to use y equals mx plus b in order to come up with my equation of my line. Well, I already know m, I need to find b. So what I'm going to do is I'm going to use the information that I'm given. I know my m, and although I gave these a subscript, I could use either of these points and put it in for x and y because I know this line has to pass through both of these points. And so I'm going to use the point 4, 5. So I'm going to plug in 4 for x and 5 for y. 12 plus b equals 5. I subtract 12 from both sides, and I get b equals -7. And so my equation of my line would be y equals 3x minus 7. All right, that's the way we can do this using this equation here, right? Now, some people don't like using that equation because you actually have to do work to find b, although the work is not that hard to find b. If you don't want to solve an equation or solve an equation for a variable, then you can use the point slope form, right? Because I already have my m, and using either of these points, now I know I labeled this one x1, y1, but as long as I use any point that the line passes through, I can substitute it in for x1 and y1 in order to come up with the equation of a line. And since we already have these 2 points, I'm going to do that. Now, just for fun, I'm going to use the 2 and a -1. I'm going to plug in, so that means I have an x1 and a y1. Now, I'm using x2, y2. It doesn't matter. You're going to get the same result, all right? So I'm going to plug in y1, -1 for y1. My slope is 3, and corresponding to that point, I have an x-coordinate of 2. So this becomes a y plus 1 equals 3x minus 6. Now, although this is an actual equation, we like to leave our equation in this form here where y is on one side by itself for the simple fact that we know that this is a function. So we could write this as f of x equals 3x minus 7. So a lot of times, although we use this method here, we go until we have y isolated by itself. So if I subtract 1 from both sides, we'll see that we get the exact same equation. All right, so either way, you don't have to use both of these methods to come up with the linear function. Only use one of them, whichever one you prefer. I'll never tell you, oh, use the point slope form or use the slope intercept form to come up with the equation of a line. The choice is yours. Our last example today has to do with a numerical example with a real life example, a real world problem. Says the percentage of people P below the poverty level in the United States is given in the table. Notice my input variable is T. The input variable is normally always given on top. T represents the year since 2000, and my output variable is P, which is a percentage. It represents the percentage of people who are living below the poverty level in the United States. Part A, determine if the data represents P as a linear function of T, right? So can I write this as P equals F of T? Is it linear? Well, notice our X values are going up by 1 unit, so that's a constant. My X's are going up by a constant. If it is a linear, then my Y's also have to go up by a constant. Well, 11.3 to 11.7 is plus 0.4. 11.7 to 12.1 is plus 0.4. That's plus 0.4. So based off of this information here, I'm going to say, yes, it is linear. P is a linear function of T because as T increases by 1 year, P increases by 0.4, and I'm going to say percentage points. All right, so it's going up by a certain number of percentage points. So from 11.3% to 11.7% is plus 0.4 percentage points. It's not increasing by a percent, it's increasing by percentage points. I don't want to get too bogged down into the difference between percentages and percentage points, but I'm going to use the word percentage points here to be extra careful. And so now that we have that, we're going to find a formula for the percentage in poverty as a function of time in years since 2000, right? Well, we can go back to one of our functions, y equals mx plus b, our linear equations. And remember, m is your slope and b is your vertical intercept, right? But we don't have y and x. So what I'm going to do is I'm going to change my variables to match my application problem. And our goal is to find m and find b, and we'll have our actual equation there. Well, if we look here, some information is given, right? Now, I went to the interpretation. I'm going to go back to that interpretation of your slope. Slope is a rate of change. It tells us how much the output increases or decreases for a 1 unit increase in our input. So every time x increases by 1, our y increases by the slope. Well, notice here, our input, our x, our t here, is increasing by 1, and our y values are increasing by 0.4. So guess what? Our slope is 0.4, all right? Now, our vertical intercept, let's go back to the definition of a vertical intercept. It's the point where your graph crosses your vertical axis, right? Every point on your vertical axis has an x coordinate or input value of 0. Well, if I look at my table, oh, there's an input value of 0, so my vertical intercept is the output. So my b equals 11.3. So I didn't have to do all of that work. Now, notice I have my m and my b here. Here, what I would have to do, I didn't do all of this stuff that I did here, right? Because I didn't have to do that because I was able to reason through what my m and my b are. Now, what you could have done is, okay, you have an input and an output. You could use the point, I'm going to come over here, 0, 11.3, and you can use the point 1, 11.7. Just pick 2 points, and you can basically do this example exactly the same as the last example here. But if we use our knowledge of what we're given and the relationships and the interpretability of our functions, our linear functions, we don't have to always do all of that work. And so I get p equals 0.4t plus 11.3. So we have our linear function. Now we're going to interpret our slope. Here's the interpretation, right? Remember, we said that the slope is your increase. If you increase every time you increase your x's by 1, the slope tells you how much your y increases, right? So I'm going to say every year since 2000, right? Because t is my input value, and it represents the number of years since 2000, right? Every year since 2000, our output, or our y, the percentage of people in the U.S. below the poverty level, is our increases by 0.4 percentage points. All right, that's the interpretation of my slope. Some key things here. You have to say something about the increase or decrease in your, the 1 unit increase in your input variable. That's why I say every year since 2000, because my input variable is years since 2000. You want to say something about your y value. So I just wrote the words that corresponds to what my y value represents. It's the percentage of people in the US below the poverty level. I need to see the word increase or decrease. Okay, so that's bold there. And I need to see, get the actual value of your slope. Now, I want to do something else here. The units of my slope. I didn't ask for the units here, but my slope has the following units. The way we get our units of our slope, all right? Now, this is not taken. Our slope equals change in y, which is our p, over the change in x, which is our t. All right, the slope comes from the operation of the units comes from the operation of the units that you do, right? My change in p is in percentage. I'm just going to use the percent symbol. And t is in years. So if I want to know the units of my slope, it's going to be percentage of people per year. Or you can say percentage per year. All right, you don't have to necessarily put the word of in there. All right, let's go to the vertical intercept. All right, from our definition of vertical intercept, we said that your vertical intercept is the value of your output when your input is 0. When my input is 0, that's t equals 0. That represents the year 2000. So I'm going to say in 2000, my output, my percentage of people in the US below the poverty level is, and the output value was 11.3%, right? And this is a y value and it's in percentages, right? So I'm going to say 11.3%. All right. Last but not least, predict the percentage in poverty in 2006. Well, 2006 is 6 units from 2000, so I replace t with 6 in this function here, and I'll get p equals 0.4 times 6 plus 11.3. That's 2.4 plus 11.3, which is 13.7, and that the units here is for p represents a percent. So in 2006, we expected 13.7% of the people to live below the poverty level. And that's all for this video.